Applications of linear systems. First, we're going to look at a homogeneous system in economics. We have the Leontief input-output model. If we suppose a nation's economy is divided into many sectors, such as various manufacturing, communication, entertainment, and service industries, suppose that for each sector we know its total output for 1 year, and we know exactly how this output is divided or exchanged among the other sectors of the economy. Let the total dollar value of a sector's output be called the price of that output, and then we have this result that Leontief proved, that there exists equilibrium prices that can be assigned to the total outputs of the various sectors in such a way that the income of each sector exactly balances its expenses. So let's look at an example. We have an economy that consists of coal, electric or power, and steel sectors. And then the output of each sector is distributed among the various sectors as seen in this table here, where the entries in a column represent the fractional parts of a sector's total output. We'll denote the prices or dollar values of the total annual outputs of coal, electric, and steel sectors by P sub C, P sub E, and P sub S respectively. If possible, we want to find equilibrium prices that make each sector's income match its expenditures. So a sector looks down a column here to see where its output goes, and it looks across a row here to see what it needs as inputs. So for instance, the first row says that coal receives and pays for 40% of the electric output and 60% of the steel output. So since we call those P sub E and P sub S, then we'll have the following equation. So coal must spend 0.4 times P sub E dollars for its share of electric's output, and 0.6 times P sub S for its share of steel's output. So then this side of the equation represents the total expenses for coal, and then the total income here we want to set equal to the expenses so that we can then find the equilibrium prices. So we can set up similar equations for electric and steel. So here we have a system of equations, and to solve it we're going to move all the unknowns to the left and combine like terms, and we'll end up with a homogeneous system. So we'll end up with the following system. So we can put this into an augmented matrix, and we can now row reduce this matrix, and then we have this following matrix in reduced echelon form. So now we can write our solutions. We have the vector P, which consists of our variables P sub C, P sub E, and then P sub S. And we simply solve each one, and so we have that P sub C would be equal to 0.94 P sub S. P sub E is equal to positive 0.85 P sub S, and P sub S is free. And so if we were to pull out our variable P sub S, then we would have the vector 0.94, 0.85, and 1. So now any non-negative choice for P sub S will result in a choice of equilibrium prices. So let's say we took that P sub S was 100, meaning $100 million. Then we would have that P sub C would be equal to 94, or 94 million, and that P sub E was equal to 85, or 85 million. So the incomes and expenditures of each sector will be equal if the output of coal is 94 million electric is 85 million and steel is 100 million. So this was an economic example of a homogeneous system using linear algebra to solve. Now let's look at chemistry and balancing chemical equations. Chemical equations describe the quantities of substances consumed and produced by chemical reactions. So here's an example. When propane gas burns, the propane, which is C3H8, combines with oxygen, O2, to form carbon dioxide, CO2, and water, H2O, according to an equation of the form here. To balance this equation, a chemist must find whole numbers x1 through x4 so that the total numbers of carbon, hydrogen, and oxygen atoms on the left match the corresponding numbers of atoms on the right, because atoms are neither destroyed nor created in the reaction. So, this example, we want to look at a systematic method for balancing chemical equations. And the way we do that is we're going to set up a vector equation that describes the number of atoms of each type present in a reaction. So we're going to look at the equation we looked at before. And this involves three types of atoms: carbon, hydrogen, and oxygen. And we want to construct a vector in R3 for each reactant and product in the equation that lists the number of atoms per molecule. So we're going to say that the first element, C3H8, which is propane, would be equal to the following vector, where we have carbon is 3, hydrogen is 8, and oxygen is 0. And then we have O2, or oxygen, and so that would set up as the vector 0, 0, 2, since we only have 2 atoms of oxygen. Then we have CO2, or carbon dioxide, which would be the vector 1, 0, 2. And then we have H2O, or water, which would be the vector 0, 2, 1. So we're going to replace our elements up here with the vectors. And so we would then have this equation. x1 times the vector 380 plus x2 times 0, 0, 2 is then equal to x3 times 1, 0, 2 plus x4 times 0, 2, 1. And what we want to do is we want to make this a homogeneous system. So we want to move these two, x3 and x4, to the left side. And so when we do that, we're going to have the following. And you'll notice that as in this equation, as I moved x3 and x4 over, we subtracted them, but instead of having the negative applying to x3, I went ahead and distributed it to the vector. So we're still at plus, but each element in the vector is now negative for x3 and x4. So now we can take this vector equation and make it into an augmented matrix, and we can row reduce this to get the following. So we see here then that x4 is free, and we end up with the following set of solutions. x1 would be 1/4 x to the 4th, x2 would be 5/4 x to the 4th, x3 would be 3/4 x to the 4th, and then x4 is free. Since the coefficients in a chemical equation need to be integers, we could let x4 be 4. And then when we substitute it in, we will then end up with x1 being equal to 1, x2 being equal to 5, and x3 being equal to 3. And we would get the following chemical equation. So you'll notice that the atoms of each element on the left is equal to the number of atoms of each element on the right. And this equation would also be balanced if, say, we doubled each coefficient. But most of the time, chemists prefer to use a balanced equation whose coefficients are the smallest possible whole numbers they can be. Now let's look at one last example of an application, and we're going to look at network flows. A network consists of a set of points called junctions or nodes, with lines or arcs called branches connecting some or all of the junctions. And so here we see a network. The direction of flow in each branch is indicated, and the flow amount or rate is either shown or is denoted by a variable. So we have two basic assumptions. Number one, the total flow into the network equals the total flow out of the network. And number two, the total flow into a junction equals the total flow out of the junction. So in this example, we have a diagram showing the traffic flow in vehicles per hour over several one-way streets in downtown Baltimore during a typical early afternoon. At each intersection, we set the flow in equal to the flow out. So here's intersection A, and notice that the flow in, the arrows are going in. We have 300 and 500, so we add those together. And the flow out here is x2 and x1, so we add those together. Now we have intersection B, so the flow in is x2 plus x4, and the flow out is x3 plus 300. Intersection C, we see the flow in is 400 plus 100, and the flow out is x5 plus x4. And then intersection D, we have the flow in is x1 plus x5, and the flow out is just 600. And then we want to look at the total flow in for the entire network. And so we see we have 500 plus 300 plus 100 plus 400. So we're looking kind of around the outside edges. And that, when we add those together, is 1300. And then the total flow out, which is in blue here, we have x3 plus 300 plus 600. So we want to set the total flow in equal to the total flow out. And we can solve that then and get that x3 is equal to 400. And so this gives rise to the following set of equations. For each intersection, we are getting our variables on the left and all of our numerical values on the right and combining any like terms. So here is the set of equations for our 4 intersections and then the total flow in and out. We can set this up as an augmented matrix, which would be a 5 by 6 matrix, and we see it here. When we row reduce it, we end up with this solution, that x1 is 600 minus x5, x2 is 200 plus x5, x3 is 400, x4 is 500 minus x5, and x5 is a free variable. A negative flow in a network branch corresponds to flow in the direction opposite to that shown in the model. So since the streets in the problem are one way, none of the variables can be negative. Thus, we have the constraint that x5 is less than or equal to 500, since x4 can't be negative. So we see here that if I was to subtract x5 from 500 here for x4, x5 couldn't be anything larger than 500, or else we would get a negative number for x4. So we're limited here on what x5 can be. It has to be a number 500 or less.